grade 11s. After going through the whole finding the derivative from first principles, you would have found it quite tedious, and it certainly has its place. And if you are asked to find the derivative from first principles, that is the skill that we're asking for, and you need to know how to do it. But fortunately, as in with much of the maths that we do, there are patterns that start to emerge when we do things more and more and more, and we can start using the rule or the pattern to find a derivative rather than having to do it from first principles every single time. So I want you to have a look at this first table, and I want you to just take a couple of seconds to look to see if you can see some sort of pattern developing. Now hopefully you've noticed that where the original function is a whole number, the derived function is 0. Where the original function had an x to the power of 1 in it, then the derived function has an x to the 0. Where there's an x squared, that one's an x to the power of 1, but oh, hang on, look here, we have a 2 in front. Here we have x cubed down to x squared, but there's something else happening in the front over here. Alright, so can you start seeing there's a pattern, because 15 is 3 times 5, and the 24 is 6 times 4, and again the power goes down. So in general, we can then say if our original function is going to be x to the power of n, then f dashed of x, or our derivative, will be n, our original power, times x to the n take 1. Okay? And if our original function is going to be a constant times x to the power of n, then f dashed of x will just be a n x to the n take 1. And if our original function is just a constant number, then our derivative with respect to x is going to be 0. Alright. We can also, if we're adding two functions or two expressions, we can just add each of their respective derivatives or subtract each of their respective derivatives. And if we're multiplying a function by a constant, then the derivative is just that constant multiplied by that derivative. I'm going to leave out the product, quotient, and chain rule for now. We will come back to them, I promise. Alright, so let's have a look at finding a derivative. So if our function is f of x, x to the 8 take 3x to the 5 plus 3/5 x squared plus 7x take 2. Now watch this. Our derivative will be the number up at the top, 8x, and we take away 1 to the power of 7, minus 3 5s of 15, x to the 4, plus 2 times 3/5 becomes 6/5, x to the 1, plus 1 times 7 is 7, and the x to the 1 becomes x to the 0, so we don't have any variable there, and the 2 has got a 0 derivative. It's one line, whole derivative. It would have taken you half a page doing the limit. Alright, let's look at b. Y equals 8x to the negative 1. So y dashed is going to be, okay, we're going to multiply by the negative 1, so negative 8x. Now be careful, negative 1 take 1 is negative 2. Okay, let's look at c. F of x is 3 divided by 2x to the 5. Now be careful, we have only learnt a definition of for a derivative when working with x to the power in a numerator, not in the denominator. But thankfully you know your index laws, and you can rewrite this fraction as 3 over 2x to the negative 5. And once you've done that, you can find your derivative, because it will be negative 5 times 3 over 2, so negative 15 over 2 x to the negative 6. Okay, and usually we then rewrite that derivative in the same form as it was originally given to us, so negative 15 over 2x to the 6. All right, next one, y equals 4 root x. Now this is going to involve you remembering that our power, when we write it in index form for a square root, is a half. So that's equal to 4x to the power of a half. And as soon as we've written that in index form, we can very easily find our derivative. So y dashed is going to be 4 times a half x to the a half minus 1 is to the negative a half, and 4 over 2 is just 2x to the negative a half. And we would want to write it in the same form as it was given to us, so that becomes 2 over square root x. Okay, let's do that last example quickly at the same time. So that's our first derivative. And we can actually find a second derivative. So our first derivative is a rate of change of a function. And we can actually find the second derivative, which is the rate of change of the rate of change. Okay, so that's like having distance, then velocity, which is our rate of change of distance, and then acceleration, which is our rate of change of velocity with respect to time. So let's have a look how to do our second derivative. If our first function is 4x to the power of 5 minus 8x, our first derivative will be 4 fives or 20x to the 4, take 8, and our second derivative, which is written as f double dashed of x, is 20 times 4, which is 80x cubed, and that's a constant, so there is no variable there. Alright, I hope that was really satisfying. I always like to learn the short way of doing things.